Hello, this is Miss Bryant. I'm going to go over the last two pages on your midterm review. So this is going to be the review of Units 3 and 4 that we have covered over the past couple weeks. So number 30 on that second to last page says to add these polynomials together. So remember, when you're adding, we're really pretty much just looking for like terms. So if we were to find the terms that have the matching variables and exponents, the 4x squared and the 5x squared can be combined, and then the terms that only have x's can be combined. And I'm kind of going in order from the greatest exponent down to the lowest exponent. So I started with my squared terms. Now I'm looking at those x to the first power or just x terms, and then I would have those constants at the end as well. So when you get everything combined correctly, the final answer to number 30 should be 9x squared plus x plus 20. All right, the next one is about subtraction, and this is exactly the same process with a minus sign. And that minus sign is going to be distributed to the second set of parentheses. Or think about this as a -1. So maybe we're adding -1 times the entire second set of parentheses, or times that whole second polynomial. So that negative sign is going to apply to everything in that second set of parentheses. So at first, you're going to have this expression where the 8x squared is now negative or minus, the 2x is now plus 2x, and the minus 3 has now become plus 3. Then we're going to do the same exact thing that we did on the adding example where we find our like terms. Well, in this case, the 6x to the third power does not have any like terms that it can combine with because nothing else in this problem has an x to the third power. So it's going to stay the same in our final answer, and then same with the x squared term. So those are highlighted two different colors because they are different terms, so just be very careful with that. And your final answer after combining like terms for the subtraction problem will be 6x to the third power minus 8x squared minus 7x plus 4. All right, so on to multiplying. Two different methods that we've talked about for multiplying are the box method or just distributing. And so I'll do the first one with the box method, and then we'll distribute for the next. So when you are working with the box, you would want to make sure that the box is made as big as the two things, the two factors that you're multiplying together here. And so since my first multiplication piece is a binomial, my box should be 2 long, and my second piece is also a binomial, so it should be 2 tall. And then you can see how I've put the x minus 9 across the top and the 8x plus 2 on the side. So in the first box, you are multiplying 8x times x times x is x squared, and then you're multiplying -9 times 8x, which is -72x. Okay, in that second row, you're multiplying x times 2, which is 2x, and then you're multiplying -9 times 2, which is -18. The fun part about the box is that typically, as long as everything's in order the way it should be, you get these like terms on that diagonal box, which is pretty cool. So once we find those like terms and we combine them together, the final answer to this problem is 8x squared minus 70x minus 18. All right, so if we're not going to use the box method, we can use the distributive property instead. This one actually is going to have a little bit more that needs to be distributed, but let's just look at it one piece at a time. So if we start with x, that x is going to be multiplied by the 2x squared, x times -5x, and x times a positive 7. That's going to leave us with 2x cubed minus 5x squared plus 7x. Okay, then we start all over again, and we're now distributing the -3. Now please make sure to include that negative sign with the 3 when you're distributing. That's going to affect your final answer greatly. So if it's -3 times 2x squared, negative times a -5x, be careful with that one, and then -3 times 7. And that's going to give you -6x squared plus 15x minus 21. Now I've kind of stacked the two different distributive properties vertically so that we can see the combining like terms step really easily. I know typically when you do the distributive property, you just list out all your terms. This might be an interesting strategy for you to consider using though. And so the final answer can be found by combining the like terms with the negative x squares there, and you can also combine the 7x's there, and you can see which terms do not have like terms and therefore are just part of our final answer. All right, the next section is going to go into looking at patterns on tables. You guys did a great job with this part of your test, so I'm just going to kind of fly through these patterns really super quick. This first one is probably the most important anyway. So 23 to 25. Have I added, subtracted, multiplied, or divided to get from 23 to 25? Well, the thing that jumps into my head first definitely is plus 2. And then I can keep looking for an adding pattern, although 25 plus 2 is not going to work, so I'm actually adding something different this time. And then 29 to get to 35, I would be adding 6, and 35 to get to 43, I would be adding 8. Okay, now that is a changing first difference. That is a changing rate of change. And so I can't really identify the function until I look for a second pattern or a second difference. Now the second difference is going to be constant because every time I have added 2 more than the time before. And so my pattern is a second difference of that plus 2. Okay, and what type of pattern do we know that has a second difference? That function is called a quadratic function. Okay, next two tables are pretty simple. The pattern here that I'm noticing is adding each time, and from -9 to -5, I would be adding 4. From -5 to -1, I would be adding 4. Just be careful when you go from a negative to a positive. You know, -1 plus 4 would give you 3, and then 3 plus 4 would give you 7. So I definitely have a constant adding 4 pattern of that very first difference, and so this is a linear function. And then finally, the last table, I could try an adding pattern out for sure, and I don't know if any of your teachers have talked yet about what would happen if we tried to use an adding pattern, so we can look at that first. Some of these numbers that I'm adding are going to get pretty crazy pretty quick though. Like to get from 16 to 64, let's see if I subtract those, 64 minus 16 is going to be 48. And then the really big change there, if I had 256 minus 64, that one I've added 192. So honestly, finding that first difference as an adding pattern is still going to lead you to eventually find a multiplication pattern that is happening. So whether that multiplication pattern is the actual pattern on your table or if it's the pattern of your first difference, it's still going to be an exponential function. So what were we multiplying by? Like if we started over and we were like, okay, obviously it's changing really fast, it's getting bigger really fast, it must have been multiplying by 4 each time. And maybe that jumped out at you right away and you didn't have to think about the adding pattern at all. But since we are multiplying, this is definitely an exponential function. Okay, then we have a diagram. Same exact thing we were just doing, except before we can analyze a table, we have to make a table. So if you ever see something, whether it's a graph, because we're going to look at a graph later, or a diagram like this one, you need to probably organize your information in a table so that it's easier to look at the patterns. And so for figure 1, I am noticing that there are 2 squares. For figure 2, I'm just going to kind of draw on this a little bit. I notice that it's a box of 4 and then 2 extra added on, so that's 6. This one I've noticed is actually a box of 9 with 3 extra added on, so 9, 10, 11, 12. Okay, and then this one is a 4 by 4 box, which is kind of cool, with 4 more added on. So 16 plus 4 more would be 20, and we can look for a pattern. So my pattern could be to get from figure 1 to figure 2, I have added 4. To get from 6 to 12, or figure 2 to figure 3, I've added 6. And then to get from 12 to 20, I've added 8. And that looks exactly like the quadratic type of pattern that's going to have a second difference that we saw in that first table that we were looking at. So they want to know how many squares would be in figure number 6. So we would have to continue this pattern a little ways. So if I added 10 and then 12, that would keep that second difference of the plus 2 that I noticed going on. So this would be 30, and then 30 plus 12 would be 42. So if I were to draw a picture of figure number 6, it should have 42 squares altogether. All right, let's see. So that type of function is definitely quadratic. And then can we write an equation for this? Because even if you're not asked on the test to write an equation, we do want you to recognize the type of equation that goes with a quadratic function. And so honestly, one thing I've noticed really quick here is that every single one of my figure numbers has x squared, or it has the figure number squared. So 1 squared is 1, 2 squared is the 4 right here, 3 squared is 9, and 4 squared is 16. So I think I should be looking for an equation that has an x squared in it. Then we can even think about what's added on. Like this was the figure number 4 that was added on. This was the figure number 3 that was added on. This was the figure number 2, and this one had the figure number 1 that was added on. So just check out that equation. If we had an equation that said y equals, or the number of squares equals, the figure number squared plus the figure number, that would work for every single one of our examples. All of our figure numbers. Okay, in number 38, you are also given a representation that is not a table yet, and so they want to know what type of function both of these are. F of x is pretty obviously a straight line, so we don't have to think very hard about that one since, you know, it's linear if it makes a straight line, but the g of x is tricky. And there was a question similar to this on our unit test, and we might assume automatically that it looks exponential just because of the curve. But you guys know enough about parabolas now to know that they curve as well. So I really want to be careful when I'm looking at the type of function for g of x and maybe organize my information in a table first before I make that decision. So think about the ordered pairs that are on the graph starting at 0, 3. And then the next ordered pair is at 1, 4. The next ordered pair is at 2, 7. And finally, that last ordered pair up here at the top is at 3, 12. Okay, so now with those exact values from the graph, I can look for either a multiplying pattern, which would make it exponential, or a second difference pattern, which would actually make this quadratic. And so what I'm noticing is that if I add 1, I can get from 3 to 4. 4 plus 3 would give me 7, and 7 plus 5 would give me 12. That is not a multiplication pattern, that is a second difference again, and therefore this is going to be quadratic for the g of x. So just be careful not to assume what it looks like. If you are looking at a picture of a graph or a diagram, you want to organize that in a table first.